Okej, nu är klockan slagen. Hej och välkomna till denna installationsföreläsning som Isabella Concina ska hålla i ämnet experimentell fysik. Och jag hoppas jag uttalade namnet någorlunda rätt. Jag som är ordförande här idag är Mats Näström och jag är prodekan vid tekniska fakulteten vid LTU. För er som inte vet så är installationsföreläsningar, de hålls av alla professorer som har blivit professorer nu då på senaste tiden. Och de här nya professorerna de kommer att installeras nu då på lördag vid den akademiska högtiden som hålls då vid LTU. I år är den då på Kulturens hus. Och installationsföreläsningar det är någonting som ges då för att vi vanliga dödliga, vi ska få en liten inblick i grunderna inom ett forskningsområde och också smaka på lite grann vad som kan vara då forskningsfront eller state of the art som vi säger då. Föreläsningen tar någonstans 30-40 minuter ungefär. Efteråt, och jag kommer att säga till då, så finns det då möjlighet då att ställa frågor. Och Isabella kommer strax att presentera sig själv lite mer, men titeln på presentationen den kan ni se här då. Och den är ju på engelska så jag kan ju ta den på svenska då. Och det är Ljuset och materian, en kärlekshistoria i nano-tiden. Och lite grann kanske vad det kan handla om då, det är att när jordens naturresurser snabbt utarmas och världens befolkning efterfrågar en högre livskvalitet. Kräver det då att forskarna söker efter livskraftiga lösningar? Det är en fråga. Och den frågan kanske vi får svar på under den här installationsföreläsningen. Interaktion mellan ljus och materia har alltid varit spännande också. Det är väl någonting som vi kanske ibland funderar på då. Och när materia reduceras till, när vi tänker oss materia och det blir i nano-skalan, då förändras den här interaktionen mellan ljus drastiskt och det öppnar för nya perspektiv. Isabellas forskning handlar om design och tillverka extremt små material. Hon jobbar bland annat med fotodetektorer, solceller och material som kan snabba på användbara reaktioner. Så, Isabella, the stage is yours.
Thank you very much for your introduction. Good afternoon, everyone. Thank you for being here. Also, I would like to thank you, those people who are taking this lecture digitally. So let's get started. Today I would like to talk a bit together with you about one of the most classical topics in physics, which is the light-matter interaction. And we are going to take this topic from a particular perspective, which is what happens with this interaction when we work with the materials reduced at the nanoscale. But before entering the technical detail of this lecture, let me spend a few words about who I am. My name is Isabella. I was born in Venice, Italy. I have one daughter. I'm living between Sweden and Italy. I like swimming, I like reading, I like fishing. I had the chance to visit 34 countries around the world, and I could speak a few languages. I'm sorry I'm giving this lecture in English, but I know you will forgive me. Actually, I could beat Spider-Man, but my favorite superhero is definitely Batman, of course. And I was in Cuba when Fidel Castro passed away, but I had nothing to do with this, I think. And I could climb the Great Wall, I could cross the Golden Gate Bridge, and I have seen Maya ruins. So now that we made a little bit friends, let's see what I have prepared for you today. And let me start by proposing you this visionary image of our planet, the Earth, as a spaceship traveling across the universe. This idea is not mine. It was a picture of our planet proposed a few years ago by an American economist working in the Colorado University. The idea is that we, the mankind, are the passengers of this huge and fragile spaceship. And the number of these passengers is quite impressive because now we are talking about 7 billion people. And this figure increases every year by 75 million persons. So our survival strictly depends on the capability of our planet to renovate its natural capital over the time. And we know the Earth is able to do this, but the pace at which the planet can renovate its natural resources is slower than the load we are putting on it through our activities. What about this load? This load is mainly related to our need for energy. And with the word energy, I mean many things, starting from the electricity that we are using in our houses and in our workplaces, but also, for instance, the food we need to intake to keep moving. Getting energy is not priceless. There are hidden costs to pay. So let's see something about this cost. Picture on the left. This picture was taken in the US in 1970, and it represents an average American family at that time surrounded by the barrels of oil they used to need for their survival for 1 year. Now this amount has increased by 40%. What about the food? Well, I know you Swedes are pretty fond of meat, so think that to make half a ton cow costs roughly 1,000 liters of oil. And if by chance you are vegetarian, so you feel you are not touched by this figure, be aware that growing tomatoes in a greenhouse to make them available all the year around, in terms of energy, costs 5 times more than the energy you get out of eating these tomatoes. And the examples we might have are pretty many, but then we also have other hidden costs to get our energy, which are probably harder to quantify. So take a look to the right picture. That picture was taken a few years ago, just in front of the Ministry of Oil in Baghdad. And if you look at the map down there, the 70% of the oil and gas that we use as fuels nowadays are produced in a very small portion of our planet. And of course, today I don't want to enter any political discussion, but it is plain that something is happening in those countries and to the people living there. The point is that if we should take into account all these hidden costs for the energy production, the renewable technologies which we already have available nowadays will become very competitive with the traditional technologies we are nowadays exploiting to get the energy we need. And this math would be based purely on an economical point of view. But there are also other hidden costs related to the standard of life that we want to have. And of course, everybody want to have a life that is better and better. But in order to have this, we are polluting our planet a lot. Through what activities? Agriculture, industries, but also, for instance, all the healthcare system that we have is contributing to this pollution. And today we will see something about water scarcity and water remediation and water security. But if you want to know more, you can link to the homepage of the World Wildlife Organization. And there you can read this figure. By 2025, so in a few years from now, 2/3 of the world population will suffer from clean water shortage. And I don't need to tell you that most of this population live in what we call developing countries. So when I read all these figures, I was already working in university as a researcher, and a question came to my mind. Should we, as a scientist, feel the duty of taking any responsibility to help the mankind to meet these tough challenges? And of course, I was not the first scientist asking this question. More authoritative colleagues have already done this, but today I would like to quote these words written by Professor Chao Peng. This guy is a Chinese guy. He was listed among the 20 most influential chemists of the last century. And he started a brilliant career in the US working on a very specific topic that was the design and fabrication of semiconducting nanocrystals. And he got a wonderful career there up until he decided to quit and to go back to China to dedicate himself to the education of the new generations. His thinking is that thanks to the capability we have developed over the years to reduce the matter at the nanoscale, we are possibly now ready to put ourselves at the service of the mankind and of our planet to design new and smart pathways exploiting these nanomaterials to help our natural world and to find a way of living which might be more in harmony with the surroundings. Talking about energy and our energy needs, we know since many years, I would say, that we do have a clean energy source which is super powerful and basically never-ending, and this source of energy is the sun. And a projection, an estimate, published a few years ago on Science, states that the production of the energy need for the whole world population would require to cover an extremely reduced amount of our planet, 0.16%, by solar panels featuring a medium efficiency, around 10%. Now think that the solar panels we are nowadays using on our roofs have an efficiency around 20%. So this estimate is quite impressive for me. So what I thought was that I could try and do something with my research about all these problems that we have now talked about a little bit. So the idea is to go in nano to meet the sun and go in nano to clean water. Why this? Because when the matter is reduced to the nanoscale, the way it interacts with the light is drastically changed. And in particular, the optoelectronics properties of these materials can be changed. Opto here means the answer to the light stimulus, and electronics means how the electrons, which are the useful charges that we can exploit to promote useful processes, are distributed within our materials and can be transported and used. But for the ones among you who are not familiar with this nano thing, let's see how little is this nano. So we start, of course, from that wonderful dog whose height is roughly half a meter. And we go down with the size. Second picture, a fly. And there we are around 10 millimeters, which is 10 power minus 3 meters. Let's go down, and all the other pictures you can see in this slide were taken with a probe technique which is called scanning electron microscopy, which allows us to magnify quite a lot a certain specimen. So picture number 3 is the head of that fly, magnified many, many times, and the scale there is around 200 micrometers. Picture number 4, a human hair. And there we are around 10 micrometers. And if you are wondering what picture number 5 represents, well, you eat those things every day when you drink milk and you eat yogurt. Those are the so-called lactobacilli. The last picture was taken by me a few years ago, and there you can see some titanium dioxide nanoparticles which are embedding some carbon nanotubes. And the scale there is a nanoscale. We are around, the scale bar that I think you can read is 200 nanometers. So light and matter. What do I mean when I tell you that the light-matter interaction is changed when you reduce the matter to the nanoscale? Let's take this as an example. That black powder that you can see in this picture is a material, a semiconductor, which is called cadmium selenide. Black powder, nothing funny, nothing more to say about this. But if you are capable of producing the very same compound in a size range spanning from 2 to 10 nanometers, there what you can get. The colors you can appreciate are very different from the original black in the bulk status of the cadmium selenide, and each color corresponds to a precise size of these nanocrystals. Then we can irradiate with light these nanocrystals, and they answer to this stimulus by emitting radiation in other wavelengths. And there you can appreciate those wonderful colors that we can get. What about the electrons? Well, if we keep to the example of semiconductors, and you don't need to be expert in this kind of materials to appreciate these wonderful drawings. In the normal condition, the electrons within a semiconductor are sleeping in an energy condition that we call valence band. But if we can wake them up by irradiating our material, those electrons are capable of climbing an energy ladder and reach another energy state, which is called conduction band, where they can actually run. And if our material is well designed, we are able to catch those electrons and use them for our purposes. But what can we do with all these nano things? Actually, you can do many things. We can fabricate many devices, we can promote many processes, among which we can fabricate solar cells alternative to silicon. We can design materials capable of cleaning the water from pollution. We can split the water to generate hydrogen as a clean energy fuel. We can produce photodetectors, and so on and so forth. And today I will talk a little bit about some technical works I have done as for solar cells and water remediation. Just for you to know, when you design a functional nanomaterial, you need to try and improve the following: its capacity to absorb light, to generate photo-generated charges that you can exploit. You should enhance this charge generation. You should improve the extraction of those charges from this material. And finally, of course, you should improve the charge collection and use. So let's see some example designing solar cells alternative to silicon. This idea deals with what we call excitonic solar cells. And this idea was put on the table a few years ago by two scientists, Professor O'Regan and Professor Gretzel. They designed a system, was scheme you can see reported in this slide, featuring a thin film of titanium dioxide nanoparticles. Once again, we are still in the field of semiconductors, which could be sensitized with a dye, and then you can close this circuit, irradiate these materials, and generate some electricity. But in order to explain you a little bit better what we are talking about, and since I don't want you to get bored with me chatting all this time, let's look at this movie.
Oh, hi. I almost didn't see you there. Since you're here, we're going to talk a little bit about some solar panels we've been making. Solar power could be the future, but the trick to its success will be cheap, efficient solar cells made out of readily available materials. Well, we've been looking around, and there's one thing that's very readily available in America today. donuts.
Specifically the powdered kinds. Turns out these delicious little things contain everything we need to make a simple solar cell. Don't believe me? Stand back. I'm going to try some science. So, first things first. How are we going to make solar cells out of powdered donuts? Well, turns out that there's this stuff called titanium dioxide in the powder of powdered donuts. This chemical is usually used in paint to make it white, but since it also happens to be a high bandgap semiconductor, we can probably make a solar cell out of it. So, the first part is the trickiest part, getting the TiO2 out of the donuts. Try to include as little cake as possible, it's just going to make purifying it more difficult. Now take your donut powder and put it in some warm water. About 1 cup per 5 donuts should do fine. Heat it up a bit and keep it stirring for a few minutes. This will dissolve out all the useless sugar. There is a lot of it. Put your resulting white solution through any kind of fine filter. Coffee filters should do fine for this. Whatever goes through is water soluble and can be thrown away. Let the stuff remaining on the filter paper dry for a while. Now you want to fire your residual solid from the filtration. You want this to be hot enough to burn off everything organic, leaving only crystalline titanium dioxide. Self-cleaning ovens often go as high as 500 degrees Celsius. This will do fine. Now you've got titanium dioxide nanoparticles. Take it out of the oven and add some ethanol to it. High proof, preferably pure, works best. Now shake it up a bit and you're ready to make a nanocrystalline thin film. For this part you're going to need some conducting glass. Ours is indium doped tin oxide coated. Use a syringe or an eyedropper and add successive layers of your TiO2 solution. Let it dry between layers until you have a uniform white coating. So what you've got now is pretty much a solar cell. But unfortunately it won't work with regular sunlight. We've got to make it a bit more colorful so it will absorb light that we can see. Pretty much anything colorful would work. We've tried juices like raspberry, pomegranate, and red currant that seem to be okay. Chlorophyll can be purified from leaves with some ethanol, and that works as well. What we've found works best seems to be a certain kind of tea from Starbucks. Passion tea is tasty, purple, made with hibiscus, contains anthocyanins, and is very tasty. Anthocyanins are great organic dyes that have been shown to interact well with TiO2. So make a nice strong cup of tea with a couple passion tea bags. Take a little bit out and enjoy the rest. Put your TiO2 film into the tea and leave it there for a few hours. This process is called sensitization and involves the anthocyanin dyes in the tea binding with your TiO2 particles. If all goes well, after a couple hours, your TiO2 film will have turned from white to purple. Now you need to assemble the solar cell. The electricity is generated in the donut TiO2 electrode, but in order to make a complete circuit, you'll need a counter electrode. For this, take another piece of conducting glass and rub a dark pencil over the surface until you get a uniform gray coloring. You'll also need an electrolyte to make a pathway between your two electrodes. For this, add an iodine tablet, which is used as a water purifier, to a cup of high-proof alcohol, such as vodka or Everclear. Cut a hole in a thin piece of plastic or scotch tape to use as a spacer, and put this on top of your donut TiO2 electrode. Drop a very small amount of your electrolyte onto your donut electrode, and then quickly sandwich the counter electrode on top. Secure it with some clamps and you're done. So now we can test our cells and see if we can make energy on a nice sunny day. Just connect an electrical lead to each piece of conducting glass. We've connected our solar cell to a multimeter that will tell us the electric current that is being generated by our cells. We turned on the lightning setting as well just to illustrate it better for you. As we cover and uncover the solar cell to the open window, we can see a large increase in current generated by the incoming sunlight. This means that our cells are working.
And Lord, we're especially thankful for nuclear power, the cleanest, safest energy source there is, except for solar, which is just a pipe dream.
Solar isn't a pipe dream anymore. I think Homer would definitely approve of our solar cells. We can make clean, renewable energy so long as we have a supply of donuts and tea. Energy crisis solved.
Okay.
We're still brainstorming about the economic one.
Thank you for watching this video. Might sound incredible, but this video was filmed in one of the most authoritative laboratories in the world as for the light matter interaction, which is the laboratory at the Notre Dame University in Indiana, US, led by Professor Kamat, who is also enlisted among the 20 most influential chemists of the last century. Just to tell you that as scientists, we can be funny from time to time. What about this kind of solar cells? Last year, Sony started to put on the market these smart windows that you can see in this slide. So basically, you can shape this window the way you like it better. They might be also very good looking, and those windows has the capability to generate electricity when they are illuminated by the sun. Because one important point about these alternative devices to silicon technology is that they can produce electricity exploiting also diffuse light and not only direct light. So let's go a bit more technical, something that we have done in our laboratories. We had the idea to change the semiconducting materials used as electron transport materials in these solar energy converting devices and to go for zinc oxide. Zinc oxide is something that you are familiar with because it is contained in many creams that we spread on our skin. It's non-toxic and it's quite cheap to be made. One amazing thing about zinc oxide is that you can shape it the way you like better. So what we were looking for in this work was to try and enhance the light absorption capability of these materials together with an enhancement in the charge collection at one of the specific interfaces that we have when we fabricate this kind of device. And this interface is specifically the interface between the conductive substrate and the electron transport material. I didn't mention this earlier, but of course, when you generate charges with irradiation, most of these charges get lost. This process is called charge recombination, and it is public enemy number one for people like me working with this kind of materials and processes. So the idea here was to deposit a thin and transparent zinc oxide layer in between the conductive substrate and the electron transport material. And then we shaped our zinc oxide in a hierarchical fashion. So we could fabricate extremely small zinc oxide nanoparticles gathered together to form bigger particles. And these particles have the very good capability of diffusing light within these nanomaterials, increasing the probability of charge photogeneration. The idea was good, and then we went for some device engineering in order to see what the maximum photoconversion efficiency could be reached with this kind of device, and our results were pretty nice. They were advertised in this important scientific journal, which is called Angewandte Chemie, and the efficiency we could get was around 8%, which is still the world record as for the efficiency of this kind of devices. What is interesting also in this case was that all the process was carried out by using a technique which is called spray deposition, which is completely scalable for industrial production, and it's the same technique that it is used to paint our cars. Another possibility we have in order to try and enhance the capability of converting solar light into electricity by working with these devices is to improve the charge transport within the electron transport material by using graphene or graphene derivatives. And here the idea is to create a cascade energy effect among all the partners involved in making our solar energy converting devices. So we have tried this with both carbon nanotubes and graphene. I think everyone in this room is now familiar with this word after the scientists who discovered graphene got the Nobel Prize a few years ago. And here what we could get. The idea is that the carbon nanotubes or the graphene sheets can support the transport of the photogenerated charges through all the thickness of your electrode. And indeed, that was what happened here you can see once again the picture taken by the scanning electron microscope that I've shown you a few slides earlier. And what is interesting to remark from a scientific point of view in this image is that the carbon nanotubes are completely and conformally covered by the titanium dioxide nanoparticles, which is fundamental if you want to have a good charge transport. Also in this case, we had to go for some engineering of the device, some device optimization, which means controlling all the parameters of the process which is leading to the final device. And we could get a pretty nice efficiency around 9%. But let's change a little bit topic and let's go and see what we can do for water remediation purposes. I told you that we are polluting our environment. You already knew that, but what about water? Well, actually, we have many sources of contamination, resulting in many kinds of pollutants, among which organic pollutants, pharmaceutical residuals, heavy metals, and so on and so forth. So the idea is that we should be able to remediate this damage that we are creating with our human activities. And in particular, I would like to talk a little bit about the dye problem. In the picture, you can see some of the dyes that are currently used in the clothing industries. So every time you buy something that has a very nice color, very nice yellow or blue, you should think that these colors was obtained by a process which is called dyeing process using these wonderful colored powders. The problem is that this dyeing process is non-effective at all, I will say. So every year, 200,000 tons of these dyes are released in the environment. And those materials, those chemicals, are enlisted by the European Union as pollutants of priority concern. So we should design materials which are low impact for the environment and which are able to either take out of the water these contaminants or to break them down into less dangerous products. I didn't tell you this, but most of these chemicals can be cancerogenic and toxic in many ways, even in extremely reduced amounts. So my idea was that we could follow two different strategies in order to clean our water. The first is the design of water nano-adsorbents. So these materials should feature the skill of uptaking the pollutants from the water, and then we can remove also the materials from the water, which should be then cleaner. Or the other strategy we can follow is to design catalysts. A catalyst is a material which is able to speed up a certain chemical reaction by lowering the energy which is required for this reaction to occur. So let's see what we can do. In this work, the idea we got was to produce, once again, semiconductor nanoparticles, either titanium dioxide or tin dioxide, in very small size, 3 or 5 nanometers, and then to cover these spherical particles with an ultra-thin shell of another oxide that was vanadium pentoxide. And when we impose this small change to our nanoparticles, what happens is something almost incredible, because if you look at that plot, which is reporting the decrease in the concentration of a certain pollutants in water over the time, just by adding a very tiny amount of this shell second metal oxide, we could improve the removal from the water of our pollutants by more than 70%. And the reaction was also pretty fast. But exactly the same material can be exploited as photocatalyst. A photocatalyst is, once again, a material capable of speeding up a certain chemical reaction upon light irradiation. And this was what we have done with these core shell nanoparticles. And you can see once again those plots reporting the decrease in the original concentration of a certain pollutants over the time. And by optimizing the reaction conditions and the synthetic parameters leading to the final material, it was possible to increase quite a lot the percentage of the dye that was broken down by this reaction. Of course, we can also use graphene and graphene derivatives here. Most claims in literature state that graphene and its derivatives are capable of making our photo-generated charges running through the materials up to the interface with the surroundings, so to promote the reactions that we are interested in on this interface. So we tried something similar. Once again, we were working with zinc oxide and with some reduced graphene oxide. And indeed, we could verify that by using some reduced graphene oxide, it was possible to speed this degradation reaction up. Also, in this case, we had to go for some engineering of our material, especially looking at what effect the temperature that we apply when producing our catalyst has on the final reaction. So, coming to the conclusions. Today I have mentioned many words: physics, chemistry, engineering, and so on and so forth. Why this? Because if we want to go for this way, we need to adopt a multidisciplinary approach. It's no longer enough that physicists work on their own or chemists do the same on their own. We need to be able to develop a common language and work all together. So nanotechnology can be indeed applied for achieving useful devices and processes, but the problem is that even at the lab scale, the processes behind the scenes, so what is really happening behind all the data and the blah blah that I have been showing you here, is extremely complicated. So applied research is good, but basic research is still mandatory. We need to be able to understand all these complicated processes if we want to go for an effective design of functional materials. Should we feel any responsibility as scientists? I don't know. I don't think there is a universal answer to this question because research is free. So I think every one of us should be free to choose his or her own life. But I do think that we should put some thinking about what we are doing and why. So some acknowledgements. A few people working with me, the list should be much longer, but many thanks to all these wonderful persons that I met during my career. Also, acknowledgement to the money givers, without which all this work wouldn't have been possible. And of course, last but not least, thank you for being here and thank you for your attention.